Hello everyone, my name is Insen Jo and I'm from Hana University. In this video, I'm going to talk about our latest work AID. AID is short for Analytic After Engine and it's an intermediate layer between database systems and container storage device. Regardless of database systems, it enables query uploading to computation storage device. Also, it supports even HTAP environment. Then, what's HTAP? In recent years, more and more users are facing scenarios with mixed workloads rather than pure OLTP or OLAP. For example, they want a database system where the major task is transactional processing, but real-time analytics will occasionally require. We call these HTAP scenarios, and HTAP database systems generally rely on multi-version concurrency control, MVCC. Compared to the traditional OLTP-friendly MVC systems, those for HTAP face the severe concern of massive data versions and their searching overhead caused from analytic workloads. Then, let's see how HTAP's complicated computing models challenge us to handle transactions. In HTAP, as transactions continuously update target tables, a continuous stream of data versions is generated. And this induces random redundant access. More specifically, given a query on multi-version data, MVCC systems have to find visible versions of later records. Here, the visible version is the latest version that was committed at the time when the query starts. For example, suppose that versions of record C piled up. And currently, its latest version is stored in PG, and then there comes the oldest transaction and finds its visible version. To look it up, the traverser starting from PG is initiated, goes through the prior versions, and finally reach its visible version in PX. As we can see, this causes redundant random reads to PX, PY, and PG. And in many application domains, adopting additional computing resources may be a cost-effective solution to speed up work. Of course, in database systems, there have been steady approaches that integrate computation storage device into them. Is to boost analytic queries by eliminating relevant data within storage and maximize effective data transfers between storage and host. However, such integration should face an inevitable hurdle. For data access, CSD should understand database storage layout and semantics. And the prevailing solution for this is to hardwire them into FPGA. Unfortunately, each vendor has its own storage layout and semantics. As seen in these figures, the same logical records are stored in a segmented file in PostgreSQL and in SSD file in MyRax. Then, why does vendor-specific storage format become a hurdle when a database system adopts CSD? Considering the amount of FPGA logic and significant hardware development effort, it's not feasible to implement multiple vendor logics on a single FPGA. This is why most prior work supports the sole vendor and partial set of query operations. Moreover, when attempting to involve CSD in MVCC, we'll face a more critical hurdle of random redundant access caused from version traversal. Considering internal I/O performance, CSD would show good sequential read throughput, but poor random performance. And besides, compared to host memory, CSD internal memory is slower as well as small-sized. So we can say CSD is unsuitable for frequent random reads and also for version traversal. In short, there has been no CSD-enabled solution that supports multiple MVCC database systems. The burden of implementing version traversal and vendor-specific logics in CSD must be the primary cause. If so, is there no way to accomplish this? This is where our aid comes in. It's a solution that can completely release CSD from such burden. Actually, aid is an intermediate layer between MVCC database systems and CSD. For the sake of CSD, it takes charge of version search and translation from vendor-specific to vendor-neutral logics. First, it introduces host-side version pre-screening and forestalls costly version traversal in CSD. Also, for support of multiple MVCC systems, it adopts canonical interface and retains vendor neutrality. In traditional MVCC, every likely version has a version pointer. To find visible versions, MVCC systems follow version pointers and find versions satisfying query snapshots, and this causes a series of randomness. To avoid running costly version traversal, we introduce version indexes and use them for version search instead of traditional version pointers. In aid, every likely version has a corresponding version index. It's a short description of each likely version and comprises 2 items only. First, it contains mean and max timestamps that define transactions lifetime. Aid inspects timestamps and filters out tuples invisible to analytics by query snapshot. Also, it includes a version locator, which points to the physical location of each likely version. And version indexes are managed by a Unilever data file, so when a new version is generated, its version index is created and inserted into per data file version index. When operating queries, aid follows pre-screen, upload, execute model. First, it should choose all or part of a query plan to upload. Aid prefers to choose sub-plans having equijoin with filter products because it's the best effort strategy to upload query plans exhibiting high selectivity. And after deciding sub-plan to upload, aid execute the first step of pre-screen upload execute model. As already mentioned, to forestall version traversal in CSD, host-side aid takes charge of version search. For each data file related to a given query, it reads timestamps in its associated version index file and filters out versions invisible to the given query by query snapshots. And we call this version pre-screening. And pre-screened version indexes are passed to CSD because they include visible versions only. CSD can avoid costly version searching. Also, file-wise screening enables CSD to use sequential access to the target data file. Then, as the second proposed technique, let's look at detail of our canonical interface. As all of us know, a logical tuple comprises usual data columns. But when it's stored in a data file, it's transformed according to vendor-specific storage format. Given a query subplan, CSD should locate target tuples and columns included in the plan. Then, in aid-enabled database systems, how can CSD find out their locations in a vendor-neutral way? The answer is our canonical interface. It transforms engine-specific low-column offsets in the bender-neutral formats. First, it represents a tuple location as a pair of infinite offset n lengths, and this pair is stored in locator of version index. And after locating a tuple, CSD should find out locations of target columns. We want CSD able to calculate column offsets without understanding bender-specific layouts. Our canonical interface achieves this by representing column offsets using an array of column sizes and null bitmap and passes them to CSD. So, CSD can calculate column offsets with no knowledge of engine-specific semantics. For example, if the index of a target column is n, CSD can calculate its offset by summing column lengths from 0, 1 to n. We implemented 8 for PostgreSQL 12.0 and MyLux of Facebook MySQL 5.6. Also, we load bender-neutral query processing logics on Samsung Smart SSD. We use two benchmark tools, Sysbench for synthetic multi-table join queries and CHBenchmark for TPS-SH workloads. The first two graphs describe TPS-SH throughputs on PostgreSQL and MyLux. Let's look at Q11, our best query. For Q11, 8 outperforms vanilla by up to 6.76 times. As shown in this query, in vanilla PostgreSQL, as version speed up, version search overburdens PostgreSQL, so it shows constantly increasing latency. By contrast, in 8-enabled PostgreSQL, it initially has longer latency than the vanilla due to FPGA initialization cost. However, as version speed up, prescreen eliminates costly version traversal overhead, thus it can sustain processing latency. And the results on MyLux are similar to PostgreSQL. The general tendency we observe is that ISP time would stay almost the same. However, as selectivity becomes higher, 8-enabled engines get more result tuples from ISP and thus takes longer to complete the post-processing. This is why the normalized latency shows fall when on selectivity increase. And to quantify the utility of 8-enabled ISP framework, we configure vanilla PostgreSQL to use index scan and bitmap heap scan and measure normalized latencies. 8-enabled ISP will show a break-even point as random access starts dominating the query cost. And in this experiment, such break-even point was 1 minute. After the break-even point, 8-enabled PostgreSQL started to beat both access methods because of latency from vanilla suddenly increased due to the dominant version search cost. So, in this video, I presented 8. From what I understand, is the first solution that is multiple MVC systems for uploading analytics to CSD, and we achieve this by version prescreening and canonical interface. Our evaluation shows that 8 improves query latency up to 42 times on PostgreSQL and 34 times on MyLux. This is the end of my talk, and thank you for your time and attention.